All right, welcome back, everyone. We got this starter problem here. And saying change this improper fraction into a mixed number, no problem. So I take the numerator, which is 5, and I simply divide it by 4. Okay, so again, this is going to set up with the new mixed number. The denominator will not change on this, but my quotient will be the whole number. So I say over here, 4 goes into 5 once. 1 times 4 is 4. We used up 4 of those 5, which leaves me with a remainder of 1. So the one quotient, which I have here in purple, is the whole part of the mixed number, and the remainder one, which I have here at the bottom in red, is the numerator. And that right there has changed the 5/4 fraction into a mixed number. And here are our 3 objectives for 2.3 equivalent fractions. I can find fractions equal in value, but also look different. I can make them look different. And then I can determine when fractions are equivalent, but also I can simplify fractions. So, yeah, with that, let's get started. And this goes back to the slide. We've seen it a few times. We've talked about it, even if we haven't seen it. But what we're trying to do is we're going to take fractions and make them look how we want them to look. Sometimes we're doing what the assignment wants, but usually that helps us out as well. So as it turns out, fractions can be written in different ways, but you don't actually end up changing the value. So what we do is we take the numerator and denominator, and then we multiply or divide them by the same number. So one way they've said this before is they say whatever you do to the top, you got to do to the bottom, or whatever you do to the bottom, you got to do to the top. And to give you an example of this, we'll do the example that's given there. But I like to look at it kind of like we would with a sandwich, okay? So we're going to pretend like this is a sandwich, and you got lettuce in there, or maybe some bacon strips too, or tomatoes, whatever you want. But if you took that sandwich, let's say that you did take that sandwich and you cut it in half right there. Now, what I could do is I could give you this portion of the sandwich here, which I don't really like to do this to a sandwich, but let's color it purple just so you know that this would be your part of the sandwich, but you would get 1 out of the 2 pieces, okay? The sizes of the pieces are halves, but you get 1 of them. I get the other one. I ate it already, by the way. Okay, and that would be fine. You get 1 piece out of 2 pieces, but let's say maybe there's some reason where you want maybe that sandwich right there the piece is just too big. So what you can do is you can go to the sandwich and say, you know what, let's cut this into smaller pieces. Now, if we do this, what happens is you see the shaded portion there, you still get 2 pieces, but now they're 4th size pieces. Okay, now did you get any less sandwich? And of course we're saying that the cut there makes that missing part negligible. But no, you still get the same amount of sandwich, meaning that these 2 fractions are what we would consider equivalent. Now, are there other reasons why you would split this into fourths? Yeah, maybe there's 4 people that want some. So now there's 4 pieces, and you can split it into fourths. See, so you could take your 2 pieces and give it to one person. Who knows? And if you wanted to, you could keep cutting this. So let's say you wanted to cut these in half. Okay, well then all you did is you changed the size pieces into eighths. You could count those there. But now if you got half the sandwich, you would get 4 pieces. And you can work with this in any way that you'd like. You could say, well, maybe you would split it into 6, right? You could have split it into 6 and said, you still get 3 pieces out of 6. You still get the same amount of sandwich. 4 out of 8, 5 out of 10 pieces. These are all exactly the same fraction, but they're being shown differently. The most basic or simplified form is the 1/2. That's what they're usually going to be asking for on this particular assignment. But the truth is, the 1/2 is the most simplified. But there could be other reasons to split this up, right? You can have your sandwich, maybe splitting it up into fourths. Maybe you do have a good reason for it, or tenths, or eighths, or whatever. But again, for the most part, they're going to be asking for something that is simplified. So here in this bottom, let's go down to this example. Find an equivalent fraction for 5/8. So if I wanted something that is equal to 5/8, which I do, I just need to make sure whatever I do to the top, I got to do to the bottom, or if I do it to the bottom, I do it to the top. So a common thing that students do, they'll just say, you know what, I'm going to take the 5 and multiply it by 2, and that would give me a new numerator of 10. And then I can multiply the denominator by 2, which would be 8 times 2 is 16. So you get this fraction, 10/16. It's exactly the same value of 5/8. Now, I multiplied those by 2, but again, what did you want to multiply it by? That's up to you. Okay, so here you could have said, you know what? My 5/8, I'd like to multiply the 5 by, let's say, 5. Because you get to choose. It didn't say it had to have any specific value, so in the numerator, 5 times 5 would be 25. But since I multiplied the numerator by 5, I also must multiply the denominator by 5, and I get 40. This 25/40 has exactly the same value as 5/8, just as it has the same value of 10/16. Now, that's a couple examples, and that's really all that I think that'll last for on the assignment, but one that's easy for me. So I'm going to show you this one. Let's say we started with the 5/8, okay? If I wanted something equivalent to it, and I just wanted to make this as easy as possible, what I would do is I would take the 5 and the 8, and I would multiply them by something easy like 10. Because if I multiply by 10, really all you do is you take the 5/8 and you just tack zeros on to both the numerator and denominator. And yeah, 50/80 is still the same exact value as 5/8 because, and this is called scaling. We're scaling both the numerator and denominator. So we're making the pieces smaller, but we're also getting more pieces. Now, is this all that's equivalent to 5/8? No, there's an infinite number of values you can use, but they need to correspondingly be the same value as 5/8. Now, you'll keep in mind, in order to get equivalent fractions, no matter which fraction you're looking at, if you want something that is equivalent to it, you must be using either multiplication or division. Addition and subtraction won't work because, and this is kind of what we're getting to. This is the scaling stuff. So a problem like this one, look, it's a little different. Okay, so we're saying find an equivalent fraction to 1/6. But what we need is a denominator of 18, so that's the bottom number in our fraction, of course. So if that was going to happen, we know that we're dealing with the 6 and the 18 on the bottom. What did we do to 6 in order to get this 18? Well, the 6 is being made bigger, and the only two operations, just like we saw 2 slides ago, that we can use is multiplication and division. So 6 is being made bigger. That tells me that I must multiply 6 by something in order to get 18. Now I know if I do that to the bottom or denominator, I'm also going to have to do it to the numerator, which will then get me my new numerator. Well, 6 times what is 18? Well, that would be 3. So again, I would have to multiply the 1 by 3 in order to get my new numerator, which would be 3. So the equivalent fraction to 1/6 with a denominator of 18 is 3/18. There we go. So a fact family actually may come in pretty handy for a problem like this one. The idea is still the same. We want an equivalent fraction, but they've already given us a denominator of 85. Let's make this a little bigger so we can work with it. So again, I have the same values in the denominator, and we'll look at a, I think it's module 5 on how to solve these without having to look at this scaling stuff. But 5 is being made bigger into 85, so I know that I'm going to have to use multiplication on 5 in order to get my 85. Now, whatever I multiply the 5 by in the bottom, I'll multiply the 7 by in the top, and that will give me the new numerator. But what do I multiply 5 by to get 85? Well, that's beyond our multiplication table, so a fact family may be helpful. Let's take a look at this. All right, so I'm going to move this over here. That's the multiplication problem. We're going to have to change this into division. So if I change it into division, which I will do, then the product becomes the dividend here. And then either one of the factors can be the divisor. So I just choose the 5 because that's going to be a direct calculation. This will tell me what I have to multiply. It's telling me back here what I got to multiply the 5 by in order to get 85. Well, again, I can't do that in my head. Maybe you can. But I'm just going to use long division here to divide. 85 divided by 5. Okay, well, how many times does 5 go into 8? Once. 1 times 5 is 5. When I subtract, I get 3 left over there. Okay, 5 doesn't go into 3, but if I drop the 5, it will go into 35 exactly 7 times. 7 times 5 is 35, so we end up with nothing remaining here, which is kind of what we expected. 85 divided by 5 is 17, which means the multiplication factor would be 5 times 17. So this means I know I can fill in this blank. I got to take 5 and times it by 17. That work is done to get 85, but then I've got to do 7 times 17 to get the new numerator. So let's go ahead and do that. 17 times 7, that will be our new numerator. So 7 times 7, that would be 49. But the 4 tens, I've got to carry over into the next place value. Now I have 7 times 1, which is 7. But then I've got to add the 7 to the 4 to make 11. And so that's my new numerator, by the way, 119. So these fractions are exactly the same. They have exactly the same value. The only difference is that they look different, and that's it. Same value, they look different. Yeah, sometimes that's what math is. We can make values look different, but without actually ending up changing the value. All right, you're going to see problems like this on the assignment. It says plot the fractions in a unit bar and compare. I'm going to start with the 1/3. Now again, since it's in thirds here, that means I need 2 markings, or like we saw in the last lesson, which was 2.2, that means I've got to push this twice. So what this does is it's going to, and I'm just kind of, that's not perfect, but it's fairly close. That gives me 2 markings in the shape, but it splits it into thirds. Okay, now we need 1 of the thirds. So I'm gonna demonstrate that with, just gonna shade it in. Let's see if I can do this half decent. Shade in, we'll pretend like I did a really good job there, all right? So that's 1 of the thirds. Okay, that's what we have there, 1 of the thirds. So for this one, where this one down here is in sixths, well, then I need 5 markings. Okay, so we end up with something like this. 2, 3, 4, 5. Okay, and it says here, use 2 of the sixths. Okay, that's a sixth right there. Here's another sixth. So I would need to shade those 2 sixths in order to show 2 sixths. Okay, so the full shaded area is 2 sixths, but then it says, and that would complete the problem right there for these, but then it says, are the fractions equivalent? Well, if I'd done this a little bit better, you could take, I'm going to take the bottom one, and it's not scaling anything, but you see it fits in there at the top, or you could take the top and it fits in the bottom. So since that is the case, we say yes, they are equivalent, because 2 sixths is the same as 1/3. And we've demonstrated that with the modeling there. You ate 8 out of every 11 candies in a jar. If you ate 24 candies, what fraction represents the number of candies you ate over the total number of candies? Okay, well, we are looking at a fraction here, so I am going to prepare that with a fraction line. But it says it's representing the number of candies you ate over, so the number of candies you ate has to be the top number, so I'll just label that number of candies 8. That's the top, that's our numerator. Now it's over, it says, the total number of candies. So that has to be our bottom number, total candies. So what we have here is we're going to have a fraction, but actually we're going to need 2 of these fractions. So I'm going to set one over here, and they need to be equivalent, not just because that's what the section is, but it says it wants to know, based on the first information, how it's going to affect the second set of information. So up here it says you ate 8 candies. So in my first fraction, I have 8 candies in the top because that's how many candies you ate, out of 11 total candies. It didn't say total, but it's 11 candies that were all in the jar. Now this is called a proportion when we get equivalent fractions, but equivalently or proportionally, it says here that you ate 24 candies. That's the top number here. What we don't know then is how many total candies there were in the jar. But once we find it, then it will be a fraction, which will answer the question. So we look at this and we say, okay, 8. See, now I'm on the top because I have 2 numbers on the top, and I can compare those. 8, since it's being made bigger, it's going to have to be multiplied by something in order to get the 24. And whatever we multiply the 8 by, we'll multiply the 11 by as well to get the new numerator. So 8 times what is 24? This actually is one of our multiplication facts. We don't need to use long division, although you're welcome to. That is 8 times 3 to get 24. So we multiply the denominator by 3 as well, which would be 33 candies total in the jar. And now that we have that, well, we have the fraction. What did it say? The fraction that represents the number of candies you ate over the total number of candies. Yep, that's it. So just to reiterate this, though, this fraction here has exactly the same value as this one. But again, now you eat more candies, which means we had to put more candies in the jar. And that is what makes this fraction have the same value as this one. Are these fractions equivalent? I think some of you could look at these two and just say, I know if these are equivalent or not. That would be fine. But I'm going to show why they are not. So yeah, I'm kind of telling you what the answer is there. So I would start at the top. I've got my 3's there, and then the 9 on the top. Okay, so I would look to use multiplication. So I would look specifically, how do I make the smaller number bigger? So we have to use multiplication, right? So I would have to take the 3, and I'd have to multiply it by 3. If I did that, if I multiplied 3 by 3, then I would get the 9. The problem is, on the bottom, if I multiply the 4 by 3, it's not 9, okay? So since it's not, if I multiply these by the same value, I do not get this fraction. That means that these ones are not equivalent. And that's it. That's all we got to do for this one. Okay, so like I said, I like to work from high to low. So you know what? I'll do this one twice. Then we'll show why it does not work. Okay, so like I said, I like to work from low to high. I may have said high to low, but you can work from high to low, meaning that I would look at this and I'd say, well, I'd have to multiply 4 by something to get 12. But then I would have to see, can I multiply 7 by the same thing in order to get 21? Well, I'll start with the 4 and 12 because that's probably easier to do in your head, but I know that 4 times 3 is going to be that 12 in the numerator. So what is 7 times 3? Well, it is 21, and since we get the same value after multiplying by the same value, then we say that these are equivalent. So up at the top, I'll just put yes. Now that's working always from low to high, but we can work from high to low, meaning I would look at the top. Again, I just start on the top. 12 is an easier number to work with than 21, in my opinion. But since I'm going from something high to something low, that means that I would need to divide 12 by something in order to get 4. And then we could say, well, 21 divided by that same number is 7. The reason why I like to go from low to high is because it's multiplication. Division tends to jack things up. Now I know that I'd have to take 12 and I would have to divide it by 3 in order to get 4. Then what is 21 divided by 3? Well, it is 7, which means that 4/7 we get from 12 21ths simply by dividing both of these by 3. Now let's say that I did 21 divided by 3, but I did not get 7. Exactly, it has to be exactly 7. If I did not get 7, then this would not have been equivalent, but it is. So our original answer stands. These are equivalent, but we've shown it now 2 ways. Now, like we talked about a couple slides ago, is, for example, 1/2 is the most simplified form of something like 2/4 or 3/6, 4/8, 5/10, and so forth. But we can do this, once again, since we are looking now to simplify, we are going to be using usually division to make that happen because we're taking values and making them lower. Okay, so whenever you're looking at simplification, we generally are using division in order to make that happen. Just the thing is, we need to remember to do it to both the numerator and the denominator. We can't just do it to one and say, oh, that's good. You have to do it to both. So we'll expect to see using division, and then we'll divide it by the same thing, and this is where our divisibility rules come back to us, and also the importance of memorizing the multiplication table as well. Because if we have all that stuff memorized, then a lot of this goes by pretty quick. And then again, if we can memorize the divisibility rules, if it's not within the multiplication table, then we can at least know what we can divide it by. But prime factorization may be helpful as well, which we will see. So just understand, we pretty much have 2 methods for simplifying fractions. You get to choose which way you like the best and then go with it. Now, when you're looking to simplify fractions, what you're going to want to do is look to divide the values by, usually it's either 2, 3, or 5. Okay, now once you simplify a fraction with 2, 3, or 5 by division, you may find that the new values in the fraction that is simplified now can still be divided by more values. If that happens, keep dividing until they can be divided no longer. Because once you can no longer divide both by the same value, then you're done. You can't simplify anymore. So here, write the fraction in lowest terms. Well, since it's telling us it's going to be lower, we are expecting to use division, not just in the numerator here, but also in the denominator as well. So I look at 18 and I look at 32, and I have to ask myself, what can I divide, because we are expecting division, both 18 and 32 by? It has to be the same value. So we look at these and we could say, you know what? I know I can divide these by 2. And that's true. You can divide them by 2. Now, without doing the long division, which is just to save time, 18 divided by 2 is 9. 32 divided by 2 is 16. Oh, actually, well, I thought that was going to need more division there. It looks like the only value I can divide these by is 2. Now, some of you, I think, are still watching the video saying, well, how do you know you can divide by 2? It was because of the 8 and the 2 and the 1's place value makes them even, which means I know I can divide them by 2. It's just once I get to 9 sixteenths rather, 9 is divisible by 3 only, and of course 9. 16 is not divisible by 9 or 3, which means that, in fact, we have found the simplified fraction. Now, just keep in mind, if you look at this value, let's say you've divided by 2, but you've noticed maybe these values can, again, be divided by 2. All right, do it. That's fine. But if you notice that they're also multiples of bigger values, then you can divide by those other bigger values. But basically, as a base, we'll be looking to divide by 2, 3, and 5. Sometimes we'll see they can be divided by 7, which is kind of weird. 11, 13, again, those are kind of weird ones. The rest of them kind of fall in place with either 2, 3, or 5. Okay, write this fraction in lowest terms. Since we're looking at lowest terms, we're going to look to division to make these numbers smaller. Okay, so once again, let's interpret this. We're making this in lowest terms. It's equivalent. It has exactly the same value, but we're going to make the numbers smaller. So, yep, division is going to happen for sure. But again, we have to ask ourselves, what can I divide 54 and also 63 by? And of course, this has to be the same exact value. Well, they're not even, so I can't divide by 2. They don't have 5 or 0 in the ones place value, so they're not divisible by 5. So here's the thing. I'm going to show you how to do this. It's going to be the same thing, but slightly different. What we would look then is, can we divide these by 3? That's the next one we should check. Well, if I looked up here at the top, I'd say, well, 5 plus 4 is 9, which means I know that I can divide by 3 because 9 is a multiple of 3. 6 plus 3 is also 9, so I know I can divide it by 3 too. So I can divide 54 by 3 and also 63 by 3 as well. And this will give me a new fraction. Well, I can show the work, which I'll do here on the right. So I do 54 divided by 3. 3 goes into 5 once. 1 times 3 is 3. When I subtract, I get 2. Drop the 4. 3 goes into 24 8 times exactly. So nothing remaining there, meaning that since I've divided 54 by 3, I get 18. Okay, well, I still got to do 63 as well. So let's go and do that. 1, 2. So 63 divided by 3. No, they're divisible by 3. 3 goes into 6 twice. 2 times 3 is 6, so that's all used up. Drop the 3. 3 goes into 3 once. So nothing remaining there. But I know that 63 now divided by 3 is 21. The problem with this is that I now know that 54 63rds simplifies to 18 21st, but I see that these two numbers also are multiples of 3. So this means I'm going to have to simplify this a little bit further by dividing 18 and 21 by 3. Now, we've already done some of the long division there. Hopefully that's a good reminder. So if you need long division, do it. But I know that 18 and 21 are fairly small multiples. 18 is the 6th multiple of 3. 21 is the 7th multiple of 3. So 6 sevenths would be considered our most simplified answer because 6 is divisible by 2, 3, and 6, but 7 is divisible by none of those. So that's as far as we can simplify this. Now, you see here how I divided by 3 and then I divided by 3 again. What this means is that if I went back to my rules, if you can remember the rule, 5 plus 4 is 9 and 6 plus 3 is 9. This means that you could have, if you wanted to, you could have divided both 54 and 63 by 9 right in the beginning. Now, the other way to do this is just to know your multiplication tables. 54 is the 6th multiple of 9, and 63 is the 7th multiple of 9. And as it turns out, that's exactly the same fraction as we got here. This one's a little less work, but it also takes a little bit more, schema, but kind of experience, a little bit more knowledge in the beginning. A little bit, I would say, experience here. Because if you already knew that 54 and 63 were both multiples of 9, or even if you remember this rule with 9s, then you could have just divided by 9. But the 3 things still works. And some students, they just don't have the experience to say, well, I know this is divisible by 9 yet. Perhaps someday you will, I don't know. But if you need to divide by 3 first and then divide by 3 again, you will get exactly the same answer. And that's my main point is I don't really care what method you use or how you get to the final answer. Of course, it should be consistent, but if you can get that answer with 2 divisions or 1 division, doesn't matter. You get the same answer. Now, what we just did was our first method. We looked for numbers that we can divide by, and then we divide both numerators and denominators by those values. So now what we're going to do is we're going to divide the numbers, but we're going to keep dividing until we can find no more primes. So we're making this, we're going to be simplifying the fractions with prime factorization. But the thing with prime factorization is if we see any values that match or are common factors in both the numerator and denominator, that's top and bottom, if we see matches, then I'm going to say we're going to cross those out, but what happens is that it becomes something divided by itself, which makes a 1. For example, okay, if we saw, because the fraction line does represent division, but if you saw something like 2 divided by 2, the truth is that you just have a 1. Now to relate this, 1 times anything, which we've seen like this, is just the same thing. Which means that we can make this what we call a phantom 1. So we can kind of erase it, and then you see that they match, right? Now that multiplied by 1 is still there, you just can't see it. That 1, if we don't see it, we call it a phantom 1. So it's still there, you just can't see it, even if we make it disappear. Okay, it's still there, you just can't see it. And that's what we mean. That's why we're trying to create ones with this prime factorization, is because if we can, then we can make it a phantom 1. It goes away. We don't have to look at that garbage anymore. So this one is exactly the same 54/63, but I'm going to be using prime factorization. Now, I would say that prime factorization, it may take a little longer. I don't care if it takes a little longer. What I need out of this is prime factors of first 54, and we will do 63. Okay, so 54, I would split up, I guess we've already seen some of the division there, but probably between 6 and 9, okay? Now, neither of these are prime, so I would split up 6 into 2 and 3, both of which are prime. And then 9 splits up into 3 and 3, both of which are prime. Now, that's all the prime factors because we've used a factor tree, and then at the end of each branch is its own prime factor of 2, 3, 3, and 3. These are all multiplied together. But then I do the same thing with 63. Okay, so again, this would be 7 times 9. Well, 7 is prime, and then 9 splits up into 3 and 3, both of which are prime. So the prime factors of 63 are 7, 3, and 3. Well, do we see any matching values in the top and bottom? Sure I do. I see this set of 3s. Now that is a 1 right there, which we will, very soon, we will ignore. But also this set of 3s, 3 divided by 3 right there would be a 1. And now I'm left with whatever's left over, which would have been 2 times 3 on the top, and then a 7 on the bottom. Well, I know, can't do anything with the 7, but a 2 times 3 right there in the top, that's a 6. And that's exactly the same fraction that we had before. So prime factorization works, or just straight division works, you get to choose. Now, one last thing about this, you get to choose, right? So you get to choose which one you like the best. Like if you're already very good with prime factorization, just keep using it. And eventually you just may be like, you know what, I know what to divide by. And that just comes with experience. But I will point out that prime factorization tends to be the most accurate way for students that are new at this. It is a little bit more work, but it will help you to see what you can call that eliminate. Some people say cancel out, but it's really just making these phantom 1s right here. So I'm recommending using prime factorization, but again, you get to choose which method you like. Okay, we're going to write this fraction in lowest terms. I'm going to do it twice with both methods. So we'll do it once, and I'll do it twice. Now we should get the same answer no matter what. I'll start with just our first method, which was just straight division, right? So we're going to look at 30 and 21. Is there a value I can divide these both by? Well, there is. I would take the 30 and the 21, and I would divide them both by 3. I know they're at least divisible by 3. Let's see if it's more, though. 30 divided by 3 would be 10. 21 divided by 3 would be 7. Boom, that's it. So now I know 30 21s will become 10 sevenths. That should be fully simplified because the 7 is prime, so it's only divisible by 1 in itself. 10 is not divisible by either one of those. Well, 1 is, but not 7. Okay, next one we're going to do with prime factorization. So I'm going to take the top number first, and we're going to write this as its expanded form multiplication, its factors. So 30, that would split up into probably 5 and 6. 3 and 10 would work, but 5 is prime. And then 6 splits up into 3 and 2. So 30 is the same as 5 times 3 times 2. 21, however, when we split this one up, it only has 2 prime factors of 3 and 7. So circle those. That ends the tree. So I would have 3 times 7. Now this one kind of purposely offset the 3's, but it doesn't matter where they are as long as there's matching values in the top and bottom. So I can take the top 3 and then match it with the bottom 3 there. And then again, these are becoming phantom 1s. Now, what am I left with? Well, in the bottom, no more left to do other than just to keep the 7. And in the top, you've got a 5 times 2. I'm probably showing more steps than most students would. But then I know that 5 times 2 in the top is going to be 10. Then, yeah, we got the 7 there on the bottom. This 10 sevenths is the same as this 10 sevenths, just in a different way. We found it in a different way. But ultimately, this is what 30/21 simplifies to, is 10 sevenths. So once again, I'll stress this as much as I can. You get to choose which of the 2 methods you like the best and then just go with that. Now, we've seen this slide before. If we ever divide by 1, you end up with the same thing, which brings us to this math rule: anything divided by 1 is itself. Now, this is an abstract way to show it. A would represent some kind of numbers like we're seeing in these examples. We're going to be seeing these as fractions. And the reason why this is important is because, well, most of the time, professors will say, this is not simplified. This is considered fully simplified because it doesn't show the divide by 1, which makes it more simplified. I think this is okay myself, just because you're still using the same method in order to get this. So maybe you start with 14 over 2, you divide them by 2 and get 7 over 1. I'm okay with that, but again, on the assignment, it probably won't be okay with it, and same with tests. So we'll have to keep that in mind. If you see anything divided by 1 as a fraction with a 1 denominator, just write the numerator out, and that would be considered fully simplified. So this one, again, well, it's just 10 divided by 1, and anything divided by 1 is itself, so the numerator 10 is the final answer here. That's considered fully simplified or in lowest terms. I'll say this: don't overcomplicate this by adding more stuff in than you need to. It just is the rule: anything divided by 1 is itself. So I think we've seen this before, maybe not with fractions, but what we get to do if we see a bunch of zeros at the tail end of a number is, and we do have to start as far to the right as we can go, but what happens is matching zeros in top and bottom, we say they cancel out, but again, it's more like they become a phantom 1. And what happens is we're breaking these values up into their multiples of 10. Now, I'm going to show that, but first let's just go through the zeros. So once again, I start as far to the right as I can go, and I see this 0, and I can match it with the 0 there on the bottom, as far to the right as I can go. I just keep going through here, okay? So this next 0, boom, I got a 0 to match there. Next, I got another 0. There's another 0, another 0, another 0. That's as many zeros as I can use, which means that just simplified as is, we have now 8,600 over 2. But what I can do now also with base 10s is, if my numerator has zeros, which it does, these zeros, I can tack that onto the answer and pretty much treat this as 86 divided by 2. So 2 goes in 8 4 times. 4 times 2 is 8. We used up all 8 there. So I can drop the 6. 2 goes into 6 3 times. 3 times 2 is 6, so nothing remaining. But my quotient there being 43 means my final answer would be 4,300. Now, some students say, well, how does this work right here? Because it's kind of like the prime factorization thing, but I'm not actually using prime factors. So what I would do is, again, I would take the non-zero numbers, like 86 and 2, and kind of keep those separated, and then the zeros tell me how many tens are being multiplied in a number. So 86, I counted 6 zeros there, so that'd be multiplied by 6 tens, 1, 2, 3, 4, 5, and 6. And then on the bottom, we had 1, 2, 3, 4 zeros, so this would be multiplied by 4 tens, like this. Now, in starting from right, going to the left, again, would have these tens here. You'd have a next set of tens, another set of tens. Again, that means that I'm dividing them to make 1. Anything divided by itself is 1. And then we got this 10 with this 10 right here. So we're left with, remember how I did 86? I did 86 divided by 2 here to get the 43. And then you just multiply by 2 more tens to tack on these zeros. So I'm showing this in 2 different ways. I would never show it this way later on. Really, I'm just going to be crossing out zeros. At least if it's necessary, you know. Now, division with 0. We have to be careful if the 0 is either the dividend or if it's the divisor. If it's in the numerator, it's the dividend. And if we end up with something like that, that's okay. 0 divided by anything is 0. Okay, so it's like saying, you know, you're going to take nothing and split it up into 5 groups, 10 groups, whatever. Well, how much does each group get? They get nothing, okay? Because you were splitting up nothing. Here, though, what we're saying is, this is really asking down here, how much 0, which is nothing, is in something? Well, how much nothing is in something? Some people say there's no nothing in something. Well, that's just not true, because there's a lot of nothing in something, and this is where we get an infinite value, which we just declare as undefined, or, well, you'll see on the assignment is just a D and E situation, okay? So it's important to understand the difference, though. If 0 is your dividend, then your quotient is 0. If 0 is your divisor, like it is down here, then it's a D and E situation. So once again, we see on these examples, I see 0 is in the numerator or the dividend, which would mean that the answer, I don't care what that denominator is, it's an 8. I really don't care what it is, it's a 0, right? Because we're splitting up 0, nothing, with 8 groups. All right, well, they each get nothing. And they can have a lot of it, by the way. This next one, with 0 being in the denominator, well, if you asked how much of nothing was in 71 somethings, well, there'd be a lot of it, so much we can't even define it, so we just say does not exist. And that concludes 2.3 equivalent fractions, so hopefully we understand how to make them simplified or in lowest terms, but also how to find equivalent fractions, and also to determine if fractions are actually equivalent. Because if you can understand that stuff, then the assignment will go very well.